Hello everyone, welcome to another video of my channel. Today we will talk about Hilbert Curve and how it is being applied to liquid clustering inside Databricks to reduce query time, especially for large data. So what is a Hilbert Curve? A Hilbert Curve is a space filling curve. In other words, even though it's only a curve, it goes through every single point in space. So here is an example of two-dimensional Hilbert curve that I have obtained from Wikipedia. All right, so let's see how we can construct a Hilbert curve from scratch. All right, so let's see how we can construct Hilbert curve from scratch and why do we care about constructing such a curve. All right, well, let's say you have a table of data, right? So we want to divide up the data into four bins or four cells like this. Two rows are in the same cells if they are extremely similar, and if they are in adjacent cell, they should be somewhat similar. And we'll want to label them in such a way that if the indices are close together, then the data on the rows in those cells should be similar or should be very close. Okay. So here is an example of a way you can label the cell, right? So this curve is called the first order Hilbert curve. But then you may say, hold on, wait a minute, right? These two cells are very close together, but yet the indices are very far apart. So how do we amend this? Well, we amend this by creating more cells, as you will see. We saw earlier that with four cell, it is definitely not enough. But we see that with 16 cells is better. So as we saw earlier, right, this cell and this cell, they are very close together, but yet the indices were 0 and 3, right? They are far apart. But if we do 16 cell, it's better, right? So instead of consider this as one single cell, we divide up into four cell, right? So we see that, okay, these indices are very close, which is very good. But wait a minute, right? These two cells are adjacent, but yet their indices are very far apart. And that's okay, right? Then we just use more and more cells. So in general, the number of cells will always be a power of 4, okay? Right, so here we see that we have a map from the indices to the cells. So in general, right, we have a map between 0 to 2 to 2n minus 1, or you can write as 4 to the n minus 1 to the cell. Now, we don't use integers, right? We're actually going to turn this into fraction between 0 and 1. The reason is that later we can use properties from topology. So earlier we saw the construction of the Hilbert curve in the finite case. How can we construct it in the infinite case so that it would go through every single point in space? Take any number in the unit interval. We define the value to be the limit of the hn of x, right? So basically we use the finite cases to construct for the infinite case. This function turned out to be well-defined, continuous, and surjective, right? Furthermore, this function is also uniformly continuous because the unit interval is a compact metric space. So here I'm using a tool from topology. Now, even though in a finite case the function is bijective, in the infinite case the function is not bijective. It is still surjective, but it is not injective. Because if it were, right, then that would imply the domain and codomain are homeomorphic, but they are not. Now, notice something here, right? We are sticking with two-dimensional space, but really you can work with any finite dimensional space, and all these properties would still be true. All right, now the next question is, how do we know how many cells to construct? So how do we find a good number of cells to use? Let's go through a specific calculation. So I already created a CSV that is about 1.14 gig. And in general, I want each cell to have about 100 meg of data. So we go to the calculation, we see that we get about 12. Now we want the number of cells to be always be a power of 4. So the closest power of 4 is 16, okay? Now, remember that x times y is the number of cells, then the number of bins on the x-axis and y-axis is the square root of the number of cells. And so we get 4 bins, right? So here we see that the n is 2, okay? Now, in general, we don't want to use equal size bin like this because if the data is heavily skewed, right, then one cell could hold a lot of data, right, while another cell would hold very little data. So what we do is we use quantile, right? All right, so now we're gonna see how to turn on liquid clustering inside Databricks and see how much it reduces query times. All right, so we are now inside Databricks. I am using Databricks through Azure. So I have already imported a CSV from Azure Blob. Here we have 4 columns. The columns date and value were created so that they are heavily skewed. Most of the dates are new, while for the value column, it was pulled from a log normal distribution. In other words, most of the values are very small or near zero. I created 2 tables. One table we will use liquid clustering, and one table without. Now notice that when I created the table, I didn't specify, whether to use liquid clustering or not. So by default, it is off. So if we look at the clustering columns, we see that it is no. Again, right, we create a same table, but then that table we will turn liquid clustering on for that particular table. All right, so let's do some queries and see where's the average runtime. So here we see that it's about 3.8 seconds. Now about 3.3 seconds. Right, so we see that on average about maybe 3.4 seconds. Okay, so earlier we created a table, but we didn't create it with liquid clustering. So now we can alter by say, okay, cluster by these 2 columns. Again, the column that you can cluster by must be nominal. In other words, the values in the column can be ordered. The date can be ordered, and the value can be ordered. Then you need to run optimize so that it will cluster the data for you. Now, if you look at the detail, now we see that the clustering columns are date and value. Okay. Now, if you look furthermore down here, you see that cluster by auto is false. If you don't want to run this thing manually every single time, and when the data change, what you do is you do cluster by auto. Then all of this will be done automatically in the background in an incremental manner. All right, so let's test the query time on the table with liquid clustering turned on. We see that it's about 2.4 seconds. Let's run it a few times. And we see that now it is sub 2 seconds. Right, and now we see that on average is maybe about 2 seconds. That's pretty phenomenal reduction in the query time. Okay, and now it's under 2 seconds. All right, thank you for joining me. I will see you guys next time.